Hi everyone, let us discuss Lagrange's mean value theorem. Okay, in previous video we have already covered Rolle's mean value theorem, and using it we are going to prove this Lagrange's mean value theorem. Let us try to understand the meaning of this theorem first, then we will discuss its proof. What have they given? We have a function f from closed interval a b to r. So what will I do? I will draw the diagram simultaneously so we can easily understand its meaning. So yes, suppose we have a closed interval AB, okay, which is subset of R. If is defined on this closed interval AB, the first condition is function should be continuous without any break. We should have a function. Yes, I have drawn it. On closed interval AB, function is differentiable. That means there should not be any corner point. Yes, the function is smooth. Then there exists C belongs to open interval AB such that f dash of C is equal to this one. Okay. In Rolle's mean value theorem, there was one more condition that f of A is equal to f of B, but that condition is dropped here. And that's why we get something different from Rolle's mean value theorem, which is f dash of C is equal to f of B minus f of A upon B minus A. So what is the geometrical meaning of it? Are you familiar with this formula? Y2 minus y1 upon x2 minus x1. This is equation of, this is formula to find slope, right, of a tangent of to a given curve. So it has the same meaning. This theorem says if you have a curve like this, if you joined this f of A, this point getting a f of A and b f of B, then there exists some point C. There exists some point C in this open interval AB such that the tangent at that point is parallel to this line. Getting? So if you join these endpoints of that curve, then definitely there is some point C such that tangent to a curve at that point is parallel to this line. This is the geometrical meaning of Lagrange's mean value theorem. So now let us discuss its proof. As I told you earlier, with the help of Rolle's mean value theorem, we are going to discuss its proof. Okay, so let me write it here. So the proof is little bit constructive. That means we should define one function. Okay, I'm defining a function. I'm defining a function phi from where to where? Close interval AB to R as, so the definition of phi is phi of x is equal to f of x plus ax. So with the help of this given function f, I have defined a new function phi. Phi of x is equal to f of x plus ax. So what is a? A is a constant. Let me mention here. Here a is a constant. Okay, it is a constant such that, but it satisfies some conditions such that phi of a is equal to phi of b. That means we should have some constant a, okay, which will satisfy this condition. Phi of a is equal to phi of b. Let us simplify this condition. Let us see what will happen. Consider phi of a is equal to phi of b. What is phi of a? At a place of x we have to put a. Let us see what will we have. F of a plus a into a. At a place of x I am putting a. Now I will put b. So we will have phi of b. So that means f of b plus ab. So let us take all terms of capital A on one side and remaining terms on another side. So here we will have a. I am shifting ab on this side. AB, f of b, I am shifting f of a on that side, f of a, right? What can we take common? We can take a common, but I will take minus a common here. Okay, so minus a, if I take minus common, you will have b minus a is equal to f of b minus f of a. So what will be value of minus a? It is f of b minus f of a divided by b minus a. I am calling it as 1. So here we got the value of capital A. Getting? So a is a constant which will satisfy this condition. We simplified it and we got the value of minus a. Okay, so this is a very important thing we have got. So yes, let us go further, but there is no more space to write. Make a screenshot of it and we will go further. So let us go further. Now let us start with a given information. What we have? We have f is continuous on closed interval AB. This is a given information. So as you know that phi is also defined with the help of f. Phi of x is equal to f of x plus x. That means f of x plus polynomial function. If it's continuous, you know polynomial function is always continuous. So that's why phi is also continuous. I can write phi is continuous on closed interval AB. So we can give same reason for differentiability also. So the given information is f is differentiable. F is differentiable on open interval AB. So we can directly write phi is also differentiable on open interval AB. The reason is phi is nothing but addition of f of x and polynomial function. Both are differentiable. That's why phi is also differentiable. So phi satisfies these two conditions. If you remember, just for 2 or 3 minutes before, I wrote here phi of a is equal to phi of b. That means capital A is a constant which satisfies that condition, phi of a is equal to phi of b. So I should mention and phi of a is equal to phi of b. So that means what we have got here, the important thing is we have got here phi is continuous, phi is differentiable, phi of a is equal to phi of b. So all these are conditions of Rolle's mean value theorem, and our phi satisfies all those conditions. So that's why I can apply Rolle's mean value theorem. So therefore, by Rolle's mean value theorem, what can we write? There exists C belongs to open interval AB such that phi dash of C is equal to, I should write phi here instead of f, phi dash of C is equal to 0. I simply use the Rolle's theorem. Let me call it as 2. But still we don't know what is phi dash of x. So let us find. So here, what is our phi? Let me write it first. Phi of x is equal to f of x plus ax, right? We are interested to know the value of phi dash. Let us find derivative. So therefore, phi dash of x, derivative addition is there. You can take separate derivative. Derivative of f of x is x dash of x, a is constant, derivative of x is 1. So that's why I got this one. So phi dash of c we want, no? Phi dash of c. Let us put c here. F dash of c plus a. Then from 2. So from 2 what can we write? Phi dash of c is equal to 0. So that's why here I can say f dash of c plus a, that is also equal to 0. But f dash of c is equal to what then? Let us shift a on that side. So f dash of c is equal to minus a. But see, in equation number 1, we have already calculated the value of minus a. So let us put it there. So from 1, f dash of c, value of minus a is f of b minus f of a upon b minus a. Simply I put the value of minus a there, okay? And yes, this is the required thing which we want. Same thing we have to prove, right? And we proved it here. So therefore we say I should mention here Cauchy's Lagrange's mean value theorem is verified. So therefore Lagrange's mean value theorem is verified. Okay, make a screenshot of it, then we will stop. Thank you. Bye bye.